Hey guys, welcome to my explanation of Euler's formula using calculus, right? Now, I made this because I'm a dummy and it didn't make sense to me. So this is probably much harder than what you need to do. All right, anyways, let's first talk about Maclaurin series approximations. We're going to need this for the proof, all right? So pretty much this looks a little bit complicated, but essentially it's just saying we have a function right now. For every we're gonna set the derivative. So we have let's try to approximate the function by putting all of its derivatives together, right? If it's like the first derivative, right? We're just gonna want the slope of the first derivative at 0, right? So we're gonna plug that in. All the other values will be 0 because they're either been derived out or they're x. There's some form of x, right? And x at 0, of course, is 0, right? That's kind of how it works. I'm not going to talk about it too much because it's kind of complicated. But anyways, let's find the series of approximations for e to the x, sine x, and cosine x. All right. So for f of x equals e to the x, right? Let's make a little table, right? For the n. So when n is 0, the 0th derivative of e to the x, or just e to the x, is of course e to the x. And e to the x of 0 is just 1, right? Now, e to the x, it's kind of special, right? In the fact that it's always the derivative of itself, right? So this is just going to be e to the x forever for every single derivative that we have, right? Which means that this number right here, this is always going to be equal to 1. So we can directly substitute that in, right? And we'll end up getting something like this. E to the x equals 1 plus 1 divided by 1 factorial times x to the 1 plus 1 divided by 2 factorial times x to the 2 plus etc. Right? Here it is formalized. For sine of x, a little bit different, right? We make the same table, right? N equals 0, n equals 1, equals 2, equals 3, right? Sine of x is just sine of x. Sine of 0 is 0, right? Derivative of sine of x is cosine x, right? Cosine of 0 is 1, right? Derivative of cosine x, that's negative sine x. Negative sine of 0 is just 0. All right, and negative sine of x, the derivative of negative sine of x is negative cosine x. Negative cosine of 0 is just negative 1, right? Okay, this seems a little bit complicated, but we can see that we're actually going to return to, if I'm making the row, right? After this, the derivative of this is just sine x again, right? That returns to 0. It's going to loop over and over, right? So that's what's going to happen, right? So if we make a few of these, right, we use the same thing we did before, except we just plug in our numbers, right? So we have 0, that just cancels everything out, right? Because anything times 0 is just 0. For the second term, we have 1, right? 1 divided by 1 factorial times x to the 1. Okay, that still works. 0, 0 cancels everything. All right, negative 1. All right, so we have negative 1 divided by 3 factorial times x to the 3. Right, that's just the same thing, right? Then that will continue forever, right? That'll loop over and over, as I was showing, right? So we can just remove the zeros, right? Sine of x equals 1 divided by 1 factorial, etc., 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 right? Because this is alternating, we're just in the statement, right? Here's the formal definition. Let me show that off, right? So we have sine of x right here, right? Here are the first few terms. As you can see, it's pretty close. We don't have infinite terms, which is why it doesn't work. Right, here's some more terms. You see, it's much better than the other one, but still, it's not infinity, so it doesn't work. For cosine x, so we have the same. It's pretty much the same thing for sine of x. We've just kind of changed it around a little bit, right? Derivatives are the same, right? If you evaluate these work out. It's pretty much the same thing. We just changed it over, right? It's also alternating. And we can show that off here, right? This is cosine x, right? Oops. Like that. Here are some of the terms, right? That's pretty close, right? All right, and that's also pretty close. But again, not perfect because we don't have an infinite number of terms, unfortunately. All right. So let's think about these approximations together, right? E to the x is a bunch of these statements, right? Sine of x is 0 plus the same statement, minus this other statement plus 0, right? And cosine of x is this statement minus this statement, right? These are identical otherwise, plus this, all right? You see, these are almost, this could almost be like e to the x, right? Is it possible to add them in some way if we exchange the variables and do some algebra so that we can get some of this going on? As it turns out, yes, it's absolutely possible. Let's consider the approximation, right, that we made for cosine of I of x, right? I just simplified this other term up here to 1 because anything to the 0 is just 1, right? So cosine of I of x is just 1 minus 1 divided by 2 factorial times I of x, because we're just directly substituting this in, right, for the other one. Let's take I out, right, so we get x squared times I squared plus, this times I to the 4, right? Of course, because it's I, we're going to see that I squared equals -1, I to the 4 equals 1, I to the 6 equals -1. That's just how I works, right? If we simplify it out, notice that the negatives, the i's right here, the negatives cancel out, while the I to the 4 is just positive, so it's still positive, right? So we end up with cosine of ix equals 1 plus this statement, plus this statement, plus etc. forever, right? Do something very similar for sine of ix, right? Sine of ix equals this, right? You bring the I terms out, right? But when you simplify the I, you kind of get left with I in this statement still, right? Which, it's fine, right? We can just divide by I, right? Boom. Now we've divided by I. I is out of the statement, and now we have this other part of our thing, right? Let's just simplify this a little bit. Just multiply the top and bottom by I, right? I times I in the bottom is negative, so -1. So the negative comes out of the fraction, comes to the top, right? All right, so now we have our final equations, right? Cosine of ix plus negative, right? Plus negative I sine ix is going to be equal to, right? 1, right? Plus this, plus the other one, etc., right? Which, if we notice from before, it's the same thing as e to the x, right? These statements are the same. So pretty much what we've done so far, we now know that e to the x is equal to cosine of ix minus I times sine of ix. This is really close, right? We just need one more step, right? And that is just substituting ix for x, right? So now we're going to replace every x in this form with equation with ix, right? So that'll give us e to the ix equals cosine I squared times x minus I times sine I squared x. All right, the negatives, I squared is just -1, right? Cosine of negative x is just cosine of x, right? And sine of negative x is just negative sine of x. The negatives cancel out, and we're left with this. Isn't that beautiful? And that's Euler's formula. Thanks for watching. Please subscribe. Let me know if this made sense or not. Bye-bye.